これの方はよろしかったですか？
はい、大丈夫です。
じゃあ失礼します。OKだと。
schemes of groups which has class number 1. When you have it, it's the same thing as the one that given by LPS, and to be honest, one is looking for application a bit more than just golden gates. There's something called super golden gates, and those are we have some construction of them, and they are actually, in order to construct them, we really needed to go to the heart of the most symmetrical object in all of number theory. I'm talking, of course, the E8 lattice. So it is explicit in the sense that we're using all the most symmetric lattices and construct from them the same way that LPS used the Gaussian integers, which they have a lot of symmetries, and yeah.
And you don't get up to 8, right?
And we get up to 4, so it's an E8, but it's overused. No. Yeah, okay, so let me just say that I do know how to say one thing about how the E8 is optimal. Well, because there's a lot of ways of saying that the E8 is the best, but you want what you really want is a group such that this guy, first of all, it's a classical definite group. So this guy is a finite group, but you want this to act transitively on let's say the neighbors, or the neighbors of a vertex, of the origin vertex in the plotted field. And this is so hard to build in nature, because I mean, this has a strict bound on the size of these groups, which are known for many time, but the number of neighbors with the plotted building grows when you're changing the prime. So you really need to take the smallest prime. You need to take the prime 2 or 3. And in 2, you need to make sure that this actually project to this group. Again, for any other prime, there's no way that you will be surjective, but you need to be surjective on this group, because this group is in some sense it enables you to go to all the neighbors in the vertex. So you really need to look at how this group on the spherical buildings, and only after that, for application, you need a nice decomposition for this group as well. But what I can say about the E8 is that you won't find a bigger group than the E8. That will be the biggest group. It will be the single group, like in your super golden gate. So.
Talk of today, and I guess most of you don't have a lot of background in reinforcement learning, so this will be a very light talk. And if you're interested in the problem and the setting and also the results, please feel free to talk to me offline. I'm Qijing. This fall I will be in IS. I'm also starting as a assistant professor in the electronic engineering department in Princeton University. And most of my PhD work actually is on understanding the foundations of machine learning theory, especially in the perspective of algorithm. Like a lot of my PhD work is on non-convex optimization. And today I would like to share some recent interest in the exploration problem of the reinforcement learning. Okay. Okay, so first, to motivate the reinforcement learning problem, I guess a lot of you have already faced a lot of the sequential decision-making problem in practice. Essentially, it's not like a single decision-making problem. You just want to make a single decision. You actually make a decision, and the environment gives you some feedback. And then you adjust and make another decision, the environment gives you another feedback. A critical example of this is like Go, and you already know the AI doing this AlphaGo is actually already being a world champion. So to solve this sequential decision-making problem, one framework is called reinforcement learning, and there's a lot of algorithms to do this reinforcement learning. Like the two main classes, one is value-based algorithm, including Q-learning. The second class is a policy gradient methods. If you don't know value-based algorithm, policy gradient, don't worry. And you only need to remember Q-learning is an algorithm. It's not like learning framework. It's an algorithm. Okay. So specifically, reinforcement learning framework assume we have an agent, we have an environment. So what we do is for each agent need to pick an action and then interact with the environment. And the environment will feedback what is the next state you transition to and what is the reward you have. Let's take this chess as an example. So the states here is actually the position of each pieces, and the action is like you want to move each piece to which position, and the reward is like after playing the game, you win, you receive the reward 1, and you lose, you receive the reward 0. So the reinforcement learning problem, you can view the problem as you want to find a good policy so that you can maximize the cumulative rewards. And in this chess way, it's like what policy is like the way how you play this chess game. So for the beginning of this talk, I will focus on the tablet setting. Just remember, tablet setting is an easier setting where we assume we have a finite number of states and actions, so that the number of states and actions is very small. Like this chess game, you only have a finite limited number of states you can possibly be there, and the action is also you don't have a very limited amount. So one very important criteria in like saying which reinforcement learning algorithm is good is in terms of those sample efficiency. Why sample efficiency is very important in practice because a lot of modern applications like you want to do Go and you want to train Atari games, usually those state-of-the-art algorithms already require millions of samples, and this takes a lot of time, like usually weeks to months to train it. And furthermore, a lot of the tasks we're still ongoing, we're trying to solve, like this robotics, we're trying to learn those folding tiles, and also those autonomous drive problems. Collecting those samples could be very expensive. For example, you don't want to crash your car, which will cost you like millions of dollars. And also it might be very time-consuming because like in this robotic case, like collecting one sample may require 5 minutes or 10 minutes. So one very basic question people would ask, since Q-learning is a very basic algorithm, has been known for a lot of years, so the first question we'd like to know is how many samples does Q-learning need to solve this reinforcement learning problems? In order to say more specifically what is Q-learning, we need to first know a very important concept called value. Essentially, value is expected reward when an agent plays start from a given state and action. For example, this is a state, and which is the position, and you can start from any action. The value kind of like reflects your belief how valuable those current states are, like what is probability you're going to win these games. And essentially, you know if you have the value, then you can just move each pieces and you see what's the value you're going to end up being, so you will pick the action which should give you the highest value. So value essentially gives you a policy and how to play the games. And Q-learning is essentially just an algorithm so that you play the games, and then you just perform stochastic updates on those values when agent interact with the environment. Okay. So me personally view reinforcement learning problem as a component of two pieces of questions. One is called planning, the other one is called exploration. Planning is essentially when you know the environment, you know how each piece is going to go and what is the reward there, you want to plan optimally. You want to know like in each scenario what is action I want to choose. But before that, you don't even know the environment. So the first problem is about exploration. Essentially exploration is instead of just knowing the environment, you want to say how should I visit all the states. For example, in this early age of like colonization, maybe your reward is kind of like which island I should colonize and which give me the highest rewards. But before that, you first need to find ways to visit all the islands.